everyone. In this video lecture, we are going to understand 8051 interrupts and interfacing applications. Under the VTU, Module 5 contains 8051 interrupts and interfacing applications. So let us see the objectives of this particular module. So first objective is to understand 8051 interrupts. Second, 8051 assembly language programming to generate an external interrupt using a switch. 8051C programming to generate square waveform on a port pin using a timer interrupt, and interfacing 8051 to ADC 0804, a DAC, LCD, and stepper motor, and their 8051 assembly language interfacing programming. So these are the contents of module 5, 8051 interrupts and interfacing applications. So let us start with 8051 interrupts. Let us understand what do you mean by interrupt, how many types of interrupts are there, how we can access the interrupts. So let us see with 8051 interrupts. An interrupt is an external or internal event that interrupts the microcontroller to inform it that a device needs its service. So this is very important as a dictionary meaning. Interrupt means disturbing. Here we are disturbing a microcontroller for its normal execution. So interrupt means an external peripheral device, or internally we are seeking a help or a task to be done by a microcontroller. So there are two types of interrupts, that is software interrupts and the hardware interrupts we call. So internally, if you are writing a program, through program or instruction, if you are interrupting the microcontroller, then we call a software interrupt. Or through hardware interrupt, means on the 8051 IC, on the pin itself, physically if you are asserting that particular pins, in that case also we can receive an interrupt to the microcontroller. So this we need to understand. An interrupt is an external or internal event that interrupts the microcontroller to inform it that a device needs its service. So you are going to put a task for a microcontroller to service. So this is what we need to understand. A single microcontroller can serve several devices by two ways. That is interrupts we call, and one more is polling. So these are the two methods how the microcontroller is going to serve the interrupts whenever an interrupt occurs. So interrupts means whenever a device needs its service, the device notifies the microcontroller by sending it an interrupt signal. So in the interrupt, it will send one signal to a microcontroller, a task to be done. So this we need to understand. So upon receiving an interrupt signal, the microcontroller interrupts whatever it is doing and serves the device. So means external peripheral device if you are connected, for example, a printer, okay, or you may be displaying something on the monitor. So all this, or if you want to connect X keypad. So in that case, the X keypad, if it is, if you are pressing any key, so that should be means how to access that or how to run the X keypad program. That we call it as an interrupt service routine. Whenever X keypad is interface with a microcontroller, that X keypad we call it as an interrupt, means it is a peripheral device if you are connecting. So whenever you are operating that, so obviously we need to run a program how to access the X keypad. So that is interrupts, means the external interrupts. So the means the program which is associated with the interrupt is called the interrupt service routine or interrupt handler we call. So whenever interrupt occurs, so microcontroller should go to the interrupt service routine and it should execute that. So this is about the interrupts. Next, polling. The microcontroller continuously monitors the status of the given device. So here what happens, microcontroller continuously will be checking the status of any peripheral device which is asking a service means service for the microcontroller. So in this case, it will be monitoring continuously. So when condition met, it performs the service. After that, it moves on to monitor the next device until everyone is serviced. So polling can monitor the status of several devices and serve each of them as a certain conditions are met. So the polling method is not efficient since it wastes much of microcontroller's time by polling devices that do not need service. So here what happens, while microcontroller is polling, means it will be waiting for the service or waiting for the interrupt to occur. So in that case, it will be idle. It will not be performing any other job. So in that case, it will be wasting its time. So microcontroller's time will be wasted in polling devices to be serviced. So this is not efficient when compared to interrupts. So that we need to understand. So this polling is done through one instruction called JNB or TF flag, especially in the timer interrupts. So jump if not bit timer flag. So it will be checking till the timer overflows. So in that case, microcontroller will not be doing any job. Just it will be waiting a TF to raise 1. So until that, it will be monitoring the TF flag. So in that case, it will be wasting its time. So we call polling is not a efficient method. So the advantage of interrupt is that controller can serve many devices, not all the same at a time. Means for that again, you need to understand interrupt at a time. Okay, each devices can get attention of the microcontroller based on the assigned priority. So you can assign a priority to the interrupts. For the polling method, it is not possible to assign priority since it checks all devices in a round robin fashion. So interrupt is having more advantage with respect to the higher priority interrupts if you want to attain first. So in that case, you have a possibility to assign a priority to a particular interrupt which is having highest priority, or it should be serviced first. So in that case, we can assign a priority. The microcontroller can also ignore a device request for service. For example, if microcontroller is doing a very important task, so in that case, it don't want to interrupt its normal execution and serve for the interrupt. So in that case, it can ignore a device request for the service. That is also possible. So we can mask the interrupt, means through instructions we can mask it, or if you are not enabling the interrupt, then so you will not be receiving any interrupts. This is not possible for the polling method again. Okay, so here whenever polling method, if you are using, you can't ignore it. It is continuously monitoring the devices. So these are the differences between the interrupt and the polling method. For every interrupt, there must be an interrupt service routine or an interrupt handler. When an interrupt is invoked, microcontroller runs the interrupt service routine. Interrupt service routine means it is a task, a set of instructions are written for servicing that particular interrupt or a particular job to be done by a microcontroller. So that will be written as a subroutine. For every interrupt, there is a fixed location in a memory that holds the address of its ISR. This is very important. A fixed memory location is allocated for writing the interrupt service routines with a particular interrupt vector. Okay, so in that we need to understand what is the space it is allocated. So the group of memory locations set aside to hold the address of ISRs is called the interrupt vector table. So knowing the interrupt vector table is very important if you are writing assembly codes. So let us see what is the procedure a microcontroller has to follow when an interrupt is occurred. So we need to know that upon activation of an interrupt, microcontroller goes through the following steps. That is very important. So it finishes the instruction it is executing, means when interrupt occurs. So the first step is it finishes the instruction it is executing and saves the address of the next instruction on the stack. This is very important. So when interrupt occurs, it branches, means it will stop there itself, means after executing that current instruction, then it will go to the interrupt service routine. Before going that, next instruction, when it comes back, next instruction is pointed by the program counter. So the program counter will be holding the next instruction in the main program. So before going to the sub program, it will store the next instruction address on the stack. That is the first point. It also saves the current status of all the interrupts internally. That is not on the stack. Current status of the interrupts will be stored internally, not onto the stack. It jumps to a fixed location in memory called the interrupt vector table that holds the address of the ISR. So after doing the first and second step, the third step will be in order to service the interrupt. So it will go to the interrupt vector table. In the interrupt vector table, you will be knowing that where your service routine for that particular interrupt is. Then it will point that address and execute that subroutine. The microcontroller gets the address of ISR from the interrupt vector table and jumps to it. So it starts executing the interrupt service routine until it reaches the last instruction of the subroutine, which is RETI, written from the interrupt. This instruction is very important. So Until that, it will be executing. Once it will come to RETI, upon executing RETI instruction, the microcontroller returns to the place where it was interrupted. This is very important, where it interrupted in the main program. So here what happens, RETI instruction will retrieve the address stored onto the stack, and it will point the next instruction in the main program. Then it will come to the main program, and the normal execution of the main program will take place. So that we need to understand. So first it gets the program counter address from the stack by popping the top 2 bytes of the stack into the PC, because 2 bytes means address is always 16-bit. Then it starts to execute from the address. So this is a procedure. Normally, whenever an interrupt occurs, a microcontroller will be followed. So let us see now how many interrupts are there in 8051. So there are 6 interrupts there, or it is allocated. First interrupt is a reset. So we know that reset, it is power up reset. It is a pin 9 in 8051 IC. In some of the books we exclude this reset because it is a normal procedure. Excluding reset, we have total 5 interrupts in 8051. So 2 interrupts are set aside for the timers, 1 for the timer 0 and 1 for the timer 1. So 2 timer interrupts will be there. Then 2 interrupts are set aside for the hardware external interrupts, that is pin number port 3.2, port 3.3 are for the external hardware interrupts, INT0, INT1 we call, that is pin number 12 and 13 of your 8051 IC pinouts. So these things you need to remember. If you exclude reset, 2 for the timers, 2 for the external interrupts, and 1 for the serial communication. That single interrupt that belongs to both receive and transfer. So knowing these interrupts are very important. So in 8051 we have total 6. If we exclude reset, then we'll be having 5. In that 5, 2 timer interrupts, 2 external interrupts, and 1 serial interrupt. So this we need to understand. So let us see the interrupt vector table, how exactly these interrupts, 6 interrupts are allocated with addresses, okay, in order to write the interrupt service routine, ISRs. So carefully observe this particular table. So reset is, upon reset, it is going to come to this address, starting address. So after this address, we have another 2 bytes. 2 bytes are there. So whenever you are writing, or if you are writing assembly code enabling the interrupts, then we should not disturb the interrupt vector memory space. That is very important. So interrupt vector memory space is varying from 0 till 23. Then 23 is for the serial communication. If you are written interrupt service routine for the 23, again it will consume some bytes. So till 30H, okay, 00 to 30H, the memory we means keep for the interrupt vector table. So in that case, we should not disturb the memory space allocated for the interrupt vector table. That is a one point we need to remember. And all of you should remember the address we use when you are writing assembly codes. So these addresses are very important. So when you are branching, or when interrupt occurs, so it should go to a interrupt service routine to this particular address. So whenever you are using a timer interrupts or external interrupts, so you need to know this. So this is you need to understand here. External hardware interrupt INT0 address is 003. This is external, so pin number 12, or if you are using a ports if you are using, so this port, on this port you can put 0 or 1. Okay, if you put 0, actually normally ports value will be high. If you put 0, so you are interrupting a microcontroller. So microcontroller will come to know that there is an interrupt coming, hardware interrupt coming on INT0. Then it will go to this particular address, and it will ISR will be written, and it will be executed. So you need to remember INT0 address is 03, INT1 address is 013. You can remember this 03013. And timer 0 is 0B, timer 1 is 1B. So 0B, 1B, that you need to remember. Then serial interrupt 0023. So 0 to 23. After 23 again up to 30H, some bytes are remains reserved for writing the serial interrupt subroutine. So this table, all of you should remember in order to write assembly code, and you need to remember the starting address of the interrupt service routine for a particular interrupts. So these are the interrupts, and these are the memory locations, and these are the external interrupts we will be using, pin number 12 and 13. Obviously, pin number 9 is for the reset. So once if you understand this, this is very important. All of you should remember the interrupt vector table. So let us see now when you are using interrupt. So you should not start your main code from the zero itself. So how to bypass interrupt vector table? So this is just means the concept you need to remember whenever you are writing assembly code with interrupts. So we need to avoid interrupt vector space or the memory space. So we write first instruction as org 0. Then we write the next ljump main. Ljump means long jump main. So main label where it is written after a 30H or anything you can write origin 30H. So obviously the control will come to here and normal execution of the main code will be written here, so that you are avoiding the interrupt vector table memory space. So you're not disturbing the ISR memory, interrupt service routine memory. So this is what we need to understand. So only 3 bytes of ROM space assigned to the reset pin. We put long jump as the first instruction and redirect the processor away from the interrupt vector table. So you're not disturbing the interrupt vector table. That we need to understand. So this is an important concept you need to remember whenever you're writing interrupts using assembly code. Always we need to write these 2 instructions first, then go to the main program with a at least 30H, starting from the 30H. So next thing is we need to understand upon reset all the interrupts are disabled, meaning that none will be responded to by the microcontroller if they are activated. So the interrupts must be enabled by the software in order for the microcontroller to respond to them. There is a register called IE that is responsible for enabling and disabling the interrupts. So this is very important. So upon reset, all interrupts are disabled. So if you are putting interrupts, or if you are expecting timer interrupts or external interrupts, if you put some interrupts, so it will not be accepted by the microcontroller unless and until if you are enabling the interrupt. So this concept is very important. So the interrupt must be enabled by software in order for the microcontroller to respond to them. So how we need to do this, how to enable? So there is a register called interrupt enable register. This is very important. That is responsible for enabling and disabling the interrupt. So so in the previous slides we discussed, you can mask them or you can unmask them. Masking means you are ignoring the interrupts. So whenever you are using this particular interrupt enable register, okay, if you write all zeros, so it will be ignored. So if you are setting a particular bits, then you will be accepting a particular interrupts. So let us see the importance of the interrupt enable register. This is very important. So whenever you are writing assembly language codes, so knowing this interrupt enable register is very important. So interrupt enable register is a 8-bit. So let us see this 8 bits. We call EX0. EX0 stands for external interrupt. ET0 external timer interrupt. Okay, this is external interrupt 1, and this is timer interrupt 1. Then ES for the serial interrupt. ET2 we are not using this. So this is enabled or disabled for timer 2 overflow or capture interrupt we call. That is used in 52, means 8952 IC. So this is very important, D7 and 6-bit it is reserved. It is not used, means it is not implemented. It is reserved for the future. EA bit is very important. We call it as a enable all. Means first, if you want to enable interrupts, first we need to make this as a high. Once if you make this high, then rest of the bits will take effect. Otherwise, this will be dummy if you are setting or resetting, okay, unless and until you make EA as 1. So EA is very important. Okay, so again you need to remember IE is a bit addressable register or byte addressable register. So all bytes you can set it or reset it, means the bits of 8-bit, or single bits also you can reset and set it. So let us see the individual bits of this 8-bit register IE. So EA, we can address it as IE.7 in order to address only this particular bit. This disables all interrupts if you make it 0. If it is enabled, all interrupts will take effect. That we need to understand. IE.6 not implemented, it is reserved for the future use. Then ET2, that is IE.5 fifth bit, enables or disables the timer to overflow or capture interrupt 8952. So these bitwise contents we need to understand. So here ES, the 4th bit, enables or disables the serial port interrupt. ET1 stands for the timer, enables or disables the timer 1 overflow interrupt. EX1, it is enables and disables external interrupt 1. ET0 enables or disables timer 0 overflow interrupt. EX0 enables or disables external interrupt 0. So these bit positions are very, very important, because whenever you are writing assembly code, if you are using only the timer 0, then you can enable only timer 0. If you are using external interrupt, then you can enable only external interrupt. No need to enable the other interrupts. So remembering the bit positions and which bit is for which interrupt is very important. So before writing any assembly codes, we need to enable the interrupts and which interrupt you are using. Either you are using a timer interrupt, or you are using an external interrupt or serial interrupt. So accordingly, we need to remember the bit positions in the IE. Then accordingly, we can configure the IE register. So remembering all the bits of IE register is very important. So let us see means to enable an interrupt, we take the following steps. So what we need to do for enabling the interrupt. So obviously bit D7 of the IE register must be set to high to allow the rest of the register to take effect. So unless and until D7 is made 1, other bits will not be means effective. So that we need to understand. So second point, the value of EA, that is if it is 1, interrupts are enabled and will respond to if their corresponding bits in IE are high. That is important. And EA equal to 0, no interrupt will be responded to even if associated bit in the IE register is high. So this is very important. So if you want to enable the interrupts, EA should be made 1. That we need to understand. So let us take one example. Through example, we can understand how to enable the interrupts. So in this example, they are asked you A, B, and C parts, okay, in order to enable a particular interrupts. So here A part, they are asked you to enable the serial interrupt, timer 0 interrupt, and external hardware interrupt. So for these 3 interrupts, so which are the bits in IE register, we need to make 1 or set that as a 1. So in B, it is we need to make the timer 0 interrupt. Okay, means we need to disable the timer 0 interrupt. So how to disable also we need to understand. Then in C, disable all the interrupts with a single instruction. So using single instruction, how you can disable all? For example, a microcontroller don't want to accept any interrupt. So in that case, how to disable all the interrupts? So those things are interrupt. So let us see the solution for this problem statement. So this is the first instruction. If you want to enable serial interrupt, timer 0 interrupt, and external INT 1 means interrupt 1 interrupt, external interrupt. So in that case, first D7 should be made 1. Then this is serial interrupt. So this is timer 0 interrupt. Then external INT 1 interrupt. This is 1. So this is how we can load the value. This is in binary. Even you can write it in the hexadecimal also. If you write in hexadecimal, it will become 96H you can write. So that enables the serial interrupt, timer 0 interrupt, and INT 1 interrupt. This is how byte you can enable, or you can do by bitwise also. Another way to perform the same manipulation is bitwise also you can set. So in order to enable the other interrupts, EA must be 1. Then serial interrupt, bitwise you are doing. Serial interrupt, if you make it 1, set bit IE.7, individual bits you are accessing. So set bit IE1, it enables the timer 0. Set bit IE2, it enables the external interrupt 1, that is INT1. So this is how we can do. It is a part, means the A part. So B, it is asked to disable or mask the interrupt 0. So clear the IE1. In previous instruction, you have enabled it. So in this instruction, if you write CLR IE.1 means you can disable this interrupt. So whenever timer 0 means timer 0 is running, so it will not be considered whenever TF flag is set. So that is the what we call it is a disabling a particular interrupt. So clearing all the interrupts means just clear the most significant bit of the IE register. So IE 0.7. So if you disable that, so all the interrupts will be disabled. This is one instruction we can use to disable all the interrupts. So this is basics about the interrupts, 8051 interrupts. There are total 5 interrupts are there, and 2 methods are there, interrupts and polling method. Polling method, continuously it will be monitoring the devices, and device by device it will be serving. And interrupts is having more advantages. If you want to accept the interrupts, or if you disable, you can do that through IE register, and total number of interrupts, interrupt vector table, and how to enable the interrupt. So these things we have learned in this particular video. So thank you for